Mackenzie, it's all up to you now.
Okay. Ready? Okay. Hi, I'm Mackenzie, and I'm going to be introducing Annie's article, Introduction to Restoring Coastal Plants to Improve Carbon Storage, Reaping What We Sow, by Irving et al. First of all, CCS is the long-term carbon capture and storage, and there's artificial and natural carbon sinks, and a carbon sink is a reservoir that accumulates and stores carbon for an indefinite period. Artificial carbon sinks are the industrial scale capture and long-term storage of anthropogenic carbon dioxide before it's released to the atmosphere as a greenhouse gas. One known method is pumping liquefied carbon dioxide into porous geological formations over a kilometer underground. There is uncertainty in the price and possible future impacts of artificial methods, like geological destabilization or long-term leakage of carbon dioxide into the environment and atmosphere. Also, establishing these methods officially might not be possible until 2025. Salt marshes, mangroves, and seagrass beds absorb large amounts of carbon dioxide from the atmosphere and store it, which decreases the effects of global warming. The carbon is then accumulated and stored over hundreds or thousands of years. This carbon is known as coastal blue carbon. In regard to blue carbon, salt marshes, mangroves, and seagrass beds play two important roles. First, there's carbon sequestration, which is capturing carbon dioxide from the atmosphere, and it's measured as a rate of carbon uptake per year. Then there's carbon storage, which is the long-term storage of carbon in plant materials or sediment measured as a total weight of carbon stored. High carbon sequestration occurs where plants convert a lot of carbon dioxide to oxygen, which is known as photosynthesis, and where there is a lot of organic matter. Wet soils are most able to store carbon because they have low oxygen levels, which slows down decomposition. Slow decomposition means that the carbon in the soil can stay there for hundreds of years. If wetlands can keep up with sea level rise, they could possibly store even more carbon in their soils because the soils will be deeper. Mangroves and coastal wetlands sequester carbon at a rate 2 to 4 times faster than tropical forests each year, and coastal blue carbon is mostly stored in the soil rather than biomass. And here's a chart which shows the carbon storage abilities of different habitat types. And the data is per unit area, and soil organic carbon and living biomass is measured as tons of carbon dioxide equivalents per hectare. And as you can see, the blue carbon altogether is able to store more carbon than the green carbon. The benefits of coastal CCS are that it's immediately available, cost-effective, publicly supported, and contributes to the preservation of biodiversity and other natural resources. Artificial methods of CCS and its impact are uncertain, so harnessing the power of coastal CCS is a natural alternative. Despite the importance of these coastal habitats, they continue to be destroyed. When these habitats are damaged or destroyed, they lose their ability to sequester carbon, and stored carbon is released, increasing the level of greenhouse gases in the atmosphere. Damaged coastal habitats then change from being net carbon sinks to net carbon emitters. Coastal habitat destruction is occurring more rapidly, and it's due to coastal development for housing, ports, and commercial stores. High nitrogen pollution can also increase the rate that carbon breaks down in coastal wetland soils. Nitrogen from septic systems, stormwater runoff, and the air are major contributors. This leads to the release of carbon dioxide and nitrous oxide, which is 300 times more powerful than carbon dioxide as a greenhouse gas. The solution to these threats is to protect and restore coastal habitats and reduce high levels of nitrogen pollution. However, Plans and goals have already existed nationally, but we are only meeting less than 3% of goals each year. All the while, wetlands continue to rapidly disappear. Hopefully something can be done to increase this percentage.
Thanks. Got it. You know what happens?
Oh, this is
My chorus teacher, I remember he sometimes would like a bomb song. It's so funny. He always puts that on that things intro.
You see how it shows up? Is that good?
Do you like to have 4 sections, or is 2 good enough? Great, excellent. Annie, take it away.
So I'm going to talk to you guys about the article that we read on blue carbon by Irving et al. Called Restoring Coastal Plans to Improve Carbon Storage, Reaping What We Sow. So the central idea in this article was carbon capture and storage, or the acronym CCS. And in the introduction, they mention artificial CCS and natural CCS. And artificial is when humans have methods to sequester carbon, and even though it can sequester large volumes of carbon, there's a lot of threatening side effects, whereas natural CCS is usually overlooked because it's not sequestering a large volume of carbon, but there's a lot of benefits to this. So this is the data that they present in the introduction of terrestrial vegetation versus coastal vegetation. So coastal vegetation, or terrestrial vegetation, is a good carbon sink, but coastal vegetation is better because the soil, as Mackenzie mentioned, is anoxic and there's limited oxygen. So as a result, they can store more carbon dioxide and they won't release it back into the atmosphere. So this is figure 1, and it shows the coastal vegetation that the article analyzes. So first we have A, seagrasses, B, mangroves, and C, salt marshes. They don't use kelp forests or macroalgae ecosystems because their soil isn't as good as absorbing and storing carbon dioxide. And then D, this is showing how when seagrass habitats are destroyed, it releases thousands to hundreds of years worth of carbon storage back into the atmosphere, which is really bad. So the purpose of the study, there's 2 objectives. The first objective was to quantify current rates of carbon capture and storage in relation to habitat decline. And the second one was to compare how rates of CCS might improve under future habitat recovery. So the methods they used, they depended a lot on past data sources. They didn't go out and collect their own data. They estimated habitat area by averaging areas from past data sources, and then they estimated CCS rate per unit area by also using past data, and they accounted for variation within habitats using a simple method of just using the highest CCS rates and then the lowest CCS rates, and then using that average. And then they found the total CCS over the past century by multiplying these two estimates, the global habitat area by the rate of CCS per unit area. And since blue carbon is a relatively new field, there's limited data available. So for the salt marshes, there's only data from the US. They have no other countries. And for future restoration, they could only use one project done for seagrasses in the US, so they had to extrapolate it to a global scale, and they didn't have any information or data for mangroves or salt marshes for the future. So this is Table 1, Part A, which summarizes habitat loss over the past century for each coastal ecosystem. So here you've got the time, they do 1879 to 1930, and then they do decade increments up to 2006. And the units are in kilometers squared. So for the seagrasses, there's a steady decline, but then in 1970, there's a dramatic decline, and it loses 44,000 kilometers squares of seagrass habitat. And then the mangrove data doesn't begin until 1970, and over the period of these 3 decades, 99,000 kilometers squared is lost. And then for the salt marshes, there's a steady decline from 1930 up until 1990. And it's important to note here that this is only data from the US, it's not global data. And then this is Table 1, Part B in the paper, and it's just showing the different CCS rates that they found for past studies, and the units are tons of carbon per kilometer squared per year, and the parentheses are just the references that are in the back of the paper. So they used the data from Part A and B to make this figure, and this is Figure 2A, and it shows the total CCS for each habitat over the past century. On the y-axis, it's years, and it starts in 1900 up till 2006, and on that y-axis, you've got the carbon capture rate, which is in tons of carbon per year, or million tons of carbon per year. So the red triangles represent the mangrove, and it starts in 1970 and steadily declines up until 2000. And in 1970, the CCS rate was 26.5 million tons of carbon per year, and now, or in 2000, it declined to 17.3 million tons of carbon per year. And then the blue circles are for the seagrass, so there's a steady CCS rate from 1920 to 1970, and then the dramatic habitat loss corresponds to a decline in the CCS rate down to what it currently is at 16.7 million tons of carbon per year. And then the green is the salt marsh, and the steady decline in the CCS rate reflects this steady decline of 5% per decade in the habitat loss. And as a result, salt marsh CCS rate is currently half of what it was in 1930. In 1930, it was 6.6 million tons of carbon per year, and now it's only 3.1 million tons of carbon per year. And then this is the final part of Table A, Part C, which summarizes seagrass restoration data and projections made based on this data. So the first 2 columns are from a seagrass restoration project done in the US in 2006, which is reference 20 in the article. And in this project, they planted 0.78 square kilograms of seagrass, but it was only 42% successful. So as a result of the 0.78 kilometers squared, only 0.33 became self-sustaining or successful seagrass habitats. And then for the final column, they took this US project and extrapolated it to a global scale and found that theoretically global restoration would result in 4.59 square kilometers of self-sustaining seagrass habitats. So this is just a number outline of Figure 2, Part B. And the authors are showing how natural recovery alone versus natural recovery coupled with different intensities of restoration would affect overall carbon capture and storage. So the natural recovery of seagrass was calculated by measures of seagrass expansion from past data, and they found a conservative rate of 1.08% per decade. And then over the next century, with this natural recovery rate, the CCS rate would be 10% above current levels. And then this table shows natural recovery coupled with restoration to different intensities. So if you just do the restoration, the current restoration is only 0.1% above natural recovery, which is pretty much nothing. And if you times that rehab by 10, it's still very negligible, really no effect. So to really have an effect on CCS rates, you need to do 100 times current restoration, which would require industrial scale restoration. So this is an illustration of that in a graph. Again, you got the years on the x-axis, the rate in million tons of carbon per year on the y-axis. The blue circles represent seagrass, CCS rate decline due to habitat loss historically, and then the outlined blue circles represent a future extrapolation of this data. So if the seagrass habitat continued to decline, that's what would happen. And then the red squares represent just natural recovery. So that would be 10% above the current CCS rates. And then the black triangles outlined are natural recovery and 10 times the current restoration. And as you can see, they're on top of each other. So timesing the current restoration by 10 would have negligible or no effect on CCS rate. So, and then to have any effect, you'd need to have industrial scale restoration to have that 9.3% increase. So in the discussion of the paper, the authors reiterate the multiple benefits of natural CCS as opposed to artificial alternatives. And even though it's a great alternative, over the past century there's been a lot of habitat loss due to human impacts, and they estimate that 434 million tons of carbon have been emitted back into the atmosphere due to this habitat loss since 1920, and this is a conservative estimate. And their figures, or figure 2, indicates that habitat restoration efforts coupled with natural recovery will have negligible effects unless it's done on an industrial scale. And they estimate it would cost about $224 million US. And so based on this, the authors do a policy evaluation, and they say instead of this industrial restoration, they should use our limited resources to just do natural recovery and prevent further habitat destruction. And they end by just saying, do natural habitat recovery on a local scale. So this is We're Excited, and thanks for listening.
Thanks, Andy.
Discussion?
Take it away.
Yeah. Okay, so this article is pretty straightforward.